Okay, today medium problem. Have a graph with nodes and edges. As the edges are directed, so only one-way direction. The nodes are numbered, and we want to find the shortest, or not shortest, but minimum path from 0 up to n-1. So each node each edge has its weight, and there is a trick or extra condition that we can do at most once on each edge or on each node. So we can go in a reverse direction of any node with double weight, like this. So this problem is kind of impossible to really take all these extra conditions into equation, because we have some questions. For example, how can we take it into account that we should do this only once? We should have some memorization or just keep track for each individual pass. We can try, we should track. This obviously would lead to n squared solutions, because to track this individual for every pass, we have to keep all these n nodes and Boolean flags for it. However, the standard Dijkstra solution is kind of makes this problem a little bit simpler. Why? Imagine we just add these extra yellow nodes, just add them, and imagine we don't have this extra condition of using only once. So remove once restriction, and Dijkstra kind of doing it automatically, because it finds effectively shortest or optimal path, and that means we wouldn't do this for every found path. We wouldn't do this twice. We wouldn't visit twice. Don't visit twice. And if we don't visit the node twice, this extra condition of using only once is automatically applied or resolved. So the Dijkstra algorithm is kind of like this. You put these nodes that you have currently in some queue, then you pull this one by one, like this, from the queue. This queue is sorted, and it always points to the shortest or smallest visited weights. This optimality allows us to not use the distance of visited node, because we already using this polling the smallest node, and we observing some nodes, and we also can put into visited set. We also can check if the extra nodes are in this visited set. There are also yellow nodes. It kind of doesn't matter. This is a reverse nodes. And we put the value into the queue. So this would be j and weight of this weight plus current weight goes to the queue. So let's look at the code. I used separate hash maps for the graph and the reverse nodes, but we can put it in the same. Now the priority queue, I use index and weight of the path and compare it by this weight. Now the polling, and I check if I add into the visited or not. And if I visit the last node, I just return, because this is optimal by the priority queue. Now I just put all the children into the queue. You can add extra check of if you visited the node or not, like B or A, but it also works without it. It just make it a little bit slower, but it's okay. So it's 300 milliseconds. Now let's look at my other solutions. A little bit logV versions. So this is only 120 milliseconds. I use array instead of hash map, because we know the number of nodes. The visited set also just integers array, and I use this check of increment visited and compare with 0. Now this is just the same while loop, and also instead of putting the pairs of custom data class, I use long and compact two values inside a single long value. It is weight and index. So this solution is kind of not very kind of fast for me. Now let's look at the rush solution. 58 milliseconds, and it is the same while loop. The Rust binary heap is max heap, so you have to do this extra minus conversions. And I did this extra check. So if visited, and this also extra check, and it improves the situation from 70 milliseconds to 60 milliseconds. So kind of 20% improvement of just one extra check. So that's it for today.